Welcome back. In this video, we will start learning about statistical inference with confidence intervals. Now, in this video, we'll learn about what an interval estimate represents, what it tells us and what it doesn't. We'll talk about confidence intervals specifically, some ways that we can calculate them and some ways that we can interpret them. We'll also introduce a concept called margin of error. Now, before we get started, I want to emphasize that in this video and in the next video, we're going to focus on the broad strokes of inference. How do we interpret these? What are some basic procedures we can use? In the units following, we'll talk about some more details in between. So let's jump in. So an interval estimate is something that is just basically a range of values based on our sample data that we've collected that consists of the most plausible or the most believable values for a population parameter. So given a set of data that we've collected, we'll come up with a range for the values that are the most reasonable for the population parameter. Now, there are a lot of different techniques that are available to us, but the one that we'll focus on in this class is what's called a confidence interval. So a confidence interval, again, is just a range of the most plausible or believable values for the population parameter based on a sample of data. Confidence intervals themselves are fairly easy to calculate, which is why they're so popular. The basic idea is that we'll take whatever our sample statistic worked out to be, and then just add and subtract some quantity, which we'll call the margin of error. Now, what this margin of error represents is how uncertain we are about the original sample statistic's accuracy. It's how far off we think we might be from the true population parameter. Think of it like the wiggle room or the uncertainty in our estimate. Our sample statistic was here, but we think the population parameter might be a little farther away. We get this margin of error based on another measure of the uncertainty in our sample, and that other measure that we use is the standard error. So if we know how to calculate the standard error for a sample statistic, we'll just calculate some multiple of that standard error, and that becomes our margin of error. That becomes what we have added and subtracted in our sample statistic. Hello, a dog has just joined us. So suppose we're interested in estimating the population mean mu. Now, based on this sampling distribution, we know that as long as our sample size is long enough and our population distribution isn't too skewed, 95% of the time our random samples will be such that if we take the mean and subtract 1.96 times the standard error, take the mean, add 1.96 times the standard error, we capture the sample statistic. Why do we know that? Where does that come from? Well, that comes to us from the fact that we're assuming that our sampling distribution is approximately normal. This looks a lot like one of those ranges that we got from the empirical rule. Now, with a little bit of algebra, what we can do is take that range, rearrange it so that the population mean mu is in the center of the range, and we get a bound on mu. So an approximate interval for the mean looks like this. We take the sample mean and add and subtract 1.96 times the standard error. Okay, so let's go back to our CDC data set from the previous video. We're pretending that we don't actually know the population mean. Based on a sample of 20,000 individuals, we got a mean of 169.683. We're assuming that's our population mean, and then we're taking subsamples from our original sample. How often should a confidence interval contain this value? Well, let's take just one subsample, the first one that we had in the previous video. It had a mean of 173.3, a standard deviation of 49, and there were 60 observations in that. So to calculate the confidence interval, we'll take the sample mean, add and subtract 1.96 times the standard error, which will look like this. We don't know what the population standard deviation is, so I'll just estimate it from my sample. So we get 173.3 plus or minus 1.96 times standard deviation over the square root of the sample size, and this is the range we get. We get a range that goes from about 160.9 pounds to 185.7 pounds. The good news is that our actual population mean, mu, which we were pretending we didn't know, is in this confidence interval. So in other words, this worked. We came up with a range that did contain the population mean. Now, we might have gotten lucky. Let's see if we did. Here's a new sample. So this new sample, again, drawn from that CDC data set, has 168.1 for the mean, standard deviation of 32, and a sample size of 60. So we still have 60 individuals in our sample. We'll calculate our new confidence interval in the same exact way. Our new confidence interval is 154.83 to 178.04. It's a little bit lower because our sample mean was a little bit lower, but look, it also contains the true population mean. So both of the samples that we took resulted in a confidence interval that contained the population mean. How often will this be the case? Well, that's where that 95% part of the 95% confidence interval actually comes into play. So what you are seeing here is a set of 100 random samples that I took from this CDC data. All of the samples had 60 observations. For all of those samples, I calculated a confidence interval. The confidence intervals that are in this sort of teal blue color are the ones that did contain the true population mean. 3 out of 100, highlighted here in this sort of color, coral color, did not. 3 out of the 100 confidence intervals missed, did not contain the true population mean. In the long run, if we have a 95% confidence interval, here's what that 95% confident actually means. That 95% confident means that we would expect about 95% of confidence intervals that are calculated in this way to be successful, to truly contain the population parameter. Now let's talk about how to interpret these things. An interpretation of a confidence interval should go something like this. We start with saying, based on our sample, every sample will result in a slightly different confidence interval, so we want to make sure to acknowledge the fact that our interval comes from one specific set of data. So based on our interval, we are 95% confident that the population parameter, whatever it is in context, is between these two values. So let's build an interval, or let's interpret, the interval that we've already calculated for the population mean weight of adults. So here's our range. We might say something like this. We might say that based on our sample, we are 95% confident that the population mean weight of all adults is between 160.89 and 185.71 pounds. Let's take a look at another example of a confidence interval. In this example, we're going to take a look at body mass index as measured by the NHANES data set, or the National Health and Nutrition Examination Survey. We have a data set that contains a random sample of 200 individuals from the 2009 to 2010 NHANES data. Let's calculate and interpret a 95% confidence interval for adult BMI. So here you can see what I've done is load the data set. This data set is called nhanes.samp. I'm using the Mosaic library to find the favstats function. I want to see how BMI as my target variable changes. The mean BMI, or the average BMI in this data set, is 126.57, so that's my sample mean. My standard deviation is 7.98. There are 190 observations here, 10 are actually missing. So using these summary statistics, let's go ahead and plug everything into our confidence interval formula. Note we are using 190 as our sample size here because 10 of our subjects did have a missing value for body mass index. We get a confidence interval that goes from 25.4 to 27.7. So based on our sample, we are about 95% confident that the population mean adult BMI for all US adults is somewhere between 25.4 and 27.7. Now, where is that 1.96 actually coming from? Well, it turns out when we introduced the empirical rule in a previous video and made the statement that 95% of values from a normal distribution were within the mean plus or minus 2 standard deviations, we were rounding a little bit to get a nice rule of thumb. Turns out that the actual probability or the actual range from a normal model that gives 95% probability in the middle is a little bit narrower. We take 1.96 standard deviations. And because we want our confidence intervals to be as accurate as possible, we'll use 1.96 instead of 2. If we want to have a different confidence level, all we need to do is change this value. Change the value that we're multiplying our standard error from. So some pretty common ones that are out there. If we want a confidence interval that works per se about 90% of the time, we can use 1.645 in our interval. If we want to work more often, if we want to be more confident with say a 95% confidence interval, we could use 2.58. So just changing the number of standard errors that we use in our margin of error calculation. For any other confidence level, we can use the standard normal distribution to find Z directly, like we did on the previous slide. Now, what happens as we change the confidence level? So what you're seeing here is what happens as we go from a 90% confidence interval to a 95% confidence interval to a 99% confidence interval. So all of these dots here represent the mean of a specific sample. We have 15 samples plotted on this graph. The interval on the very left for each sample, so the leftmost line is the 90% confidence interval. Next comes the 95% confidence interval. Next comes the 99% interval. So you can see that as we increase that confidence level, we increase or we have a wider range of values. To be more confident, we need a larger range. Now we will get plenty of practice throughout the semester calculating, working with these confidence intervals, but here we've just touched on the basic ideas. In the next lecture, we'll touch on the basic ideas of hypothesis testing. See you then.